We cooking? Yep. Okay. Yeah, sorry about Tuesday. I was in the emergency room earlier in the day. My medicine for my knee was anti-inflammatory, and it wasn't doing great things with my stomach. But yeah, it is what it is. But I'm good now. So we had a quiz up, right? How'd the quiz go? Not bad. All right, so we'll talk about the final exam. Oh, actually, let me talk a little bit about the final exam now. So the final exam is going to be all online. I'll go through and we'll talk about kind of what to expect on it today too. But it'll be your normal like 10 questions, blah blah blah. It'll be online, similar to how that quiz was. I'll probably put the time limit for it like around 3 hours or something, just in case it is acting funny or Blackboard's slow or something like that. It's going to be due by the end of, it'll be due by midnight on Saturday the 17th. So by the end of finals week, the Saturday of finals week. So you can kind of schedule it and decide when it best fits your schedule in there, that kind of stuff. I'm back not back here, but back on land by that Sunday, so I'll do all my grading Sunday and Monday because I have to have grades in by Tuesday. So that's why I'm giving you that time so you can schedule it. Hopefully that kind of makes up for me not being here. But it was a free cruise, so it's usually wouldn't have taken final exam week off. But when your brother buys you a cruise with his, you say yes. So it's a free cruise. Yeah, plus he's on the account for like paying all the onboard stuff. So all bar charges, it's fully free cruise. Yeah, I know. Oh, plus I get the initial screening of what's the name of the Star Wars movie coming out?
No way.
Because it's Disney. We're going to be on. This is a Disney cruise, and they have a movie. They have a movie theater on it, so it's free. I get to see that for free too. I might see it 2 or 3 times. Because the kids are going to be running around with their Mickey Mouse hats and stuff like that. So we'll see what happens. Huh?
Yeah, live stream that.
Outside of the Oasis of the Seas, have you been on a cruise before? Oh, the internet's not good. Yeah, the internet is crap on cruises. Like,
can we just float some cell towers out there on buoys?
But there is a new technology because we were on the Oasis of the Seas last year. Or a year and a half ago, something like that. That's actually the ship that Mr. Gonzalez got married on.
That was last year.
It was last year? Yeah. So, and they have like this new technology for cruise ship internet, and it's ridiculous. It's like a cable modem at sea. Ew.
How?
I read up on it. It uses some satellite type stuff that it keeps bouncing, but it's high speed, maybe like 40, 50 megabit per second bit.
For
Megabit.
For you? Like,
huh?
As the end user, you all the time got like.
I streamed Netflix in the spot on this thing and just watched episodes of Daredevil while I was sitting there on these it's like there's the heated stone recliner things. Just watched Daredevil for hours while my wife was walking around taking pictures of dolphins and waves and stuff.
That's how you cruise.
Yeah, exactly. Yeah, that's why we do cruises. My wife and I have very, very different tastes. We just meet up for meals. And that's it. She walks around the ship and takes pictures of all these different things, and she goes and peruses the artwork. And then she comes and tells me, like, oh, I really like this painting. And it's like a $7,000 painting. I say, oh, I'll paint you something like that. So you've seen my paintings. I made her a painting. I mean, it's legit stuff.
I was paying $7,000 for your painting.
Well, I mean, they're on sale for like $5. I mean, it's like, I think,
5,000?
no, $5. I mean, I think that's actually like less than the cost of the canvas. I mean, so really, they're not worth the canvas they're painted on. And then the art teachers at those things, they're always telling me how good my art is. Like, oh, I really like your painting, because I think they know I'm the one probably leaving the tip.
Shameless.
Yeah. I mean, look, lady, I got Teenage Mutant Ninja Turtle heads floating around on my painting. What do you mean? This doesn't look like yours? So, yeah. So she takes pictures of all the art and stuff like that. I mostly sample the various specialty drinks and go in hot tubs and stuff. And eat. Just eat ridiculous amounts of food. Oh my gosh. That's the best thing. You just ordered like 9 entrees.
Like you're not paying for it?
Well, no, it's like included. Like at the
really?
dining rooms. Oh yeah.
All
They have like a big menu. You know, they have the appetizers and then entrees and desserts. And let's say you're just debating between 2 or 3 entrees. You just order all 3. Like, I'll have this and 2 of these. Especially lobster night.
They ever roll your eyes at you?
Oh yeah. Oh yeah. But they're really cool because you usually have the same waiters every night. So they know all your drink preferences. So you show up at the table and there's already a bottle of wine there with the glasses already poured.
Quality.
Legit. Okay, so let's talk about memory. Anyway, so exam will be due by midnight on that Saturday, the 17th. What I'll probably do, just as a backup plan, in the event that Blackboard zigs when it should zag, I'll probably have a PDF version of the exam as well that I'll. That's gonna be weird. I guess whatever. Because I would put the PDF version of the exam up, which would then allow you to like basically do the exam before you start on Blackboard. Kind of just so then you have like a week to do the exam. But, I don't want to get caught in a situation where you can't do your exam because Blackboard has an issue. So that's fine. So I'll just put. I'll have the exam written by. Certainly by noon on Sunday, this coming, my plan is to maybe have it written either tonight or Saturday. I probably won't write it tomorrow. So I'll have that up and then I'll just put a PDF of the exam up on Slack. I'd prefer you do it on Blackboard so that it's easier to grade on there. But as oh my gosh, nothing's working, Blackboard failed on me, just do it and email it to me so I can get the grades in. Sound fair? So then there isn't even a time limit, I guess. It's whatever. It is what it is. So it's and then the same thing. I'll probably write the exam with the idea that you're probably going to have your notes sit in front of you. So it won't be a whole lot of like regurgitating definitions and things like that, but it'll be open book, open note because I can't keep you from using open book, open note. So I might as well say you can do it so that everybody's on the same equal footing. All right. So whatever. And then, the normal policy, if you do better on the final than you do in your midterm, I'll replace your midterm with your final exam grade. And then for those of you who showed up to the hackathon, I will apply the 10% bonus after I do the switch. So it could benefit you double. So it's, so you're going to wish you showed up to the hackathon is what I'm kind of saying. It's the thing. So that's the punchline. Okay, so let's talk for a few minutes, and then I'll go through the stuff for the exam. But so we'll kind of start talking about things that will definitely be in the exam. I'm going to work backwards because the exam will focus on the stuff we've done since the midterm. So more of the circuit stuff and the memory stuff, that stuff. But it'll also have some assembly language stuff on it. So things from before the midterm as well. So let's talk about these various RAM technologies. So effectively the quiz. So SRAM versus DRAM versus we can say flash, which is effectively solid state type stuff. So tell me about SRAM. What do we know about that guy? What's pros, cons, nature? Tell me about SRAM. Go ahead.
It's like DRAM, but it's better, more expensive.
It's like DRAM, but okay, tell me what you mean by better.
Basically, you sacrifice cost for speed and efficiency.
Okay, so it's faster. SRAM's faster. So SRAM would be kind of like our registers. That kind of stuff would be based on that. Okay, so what's the nature of it? So you say it's faster, it's more expensive stuff. So
It's
how?
like 6 to 8 transistors.
Yeah, DRAM has per one byte it has one transistor, one capacitor. That's why it has.
Okay, so 6 to 8 transistors. Why do we need to have so many transistors? What's the?
On reads to maintain the value that's there.
Okay, how do reads work? Just in general. I mean, give me the high level. I mean, so you say just to make sure it works, we have 6 to 8 transistors because reads are hard or something like that. You know, how do reads actually function?
Well, read removes the electricity from that transistor.
Okay, so to do a read actually is a sapping of the electricity. Okay, well, we kind of want to replace that. Right? You want that value to, you don't want it to be a one and done type thing. So we have 6 to 8 transistors to. This guy is to preserve the value post read. Okay, so reads are destructive, I guess I would say, but also a necessary evil, right? What's the use of having memory if we can't read from it? So it's a thing. All right, so we use six to 8 transistors, depending on the technology. Actually, some of the older technologies use even fewer transistors. Now, the fewer transistors you use, what's the implication? So why did they choose 6 to 8? What do you suspect is the reason for picking that number?
It's like how fast it's reading and how fast it can refresh the transistor.
Okay, so would you agree that maybe to some breakpoint, the more transistors, the faster you would be allowed to read from it, right? Because the more backup plans you have, right? So how many transistors does it take to refill the value? One, right? One transistor. So if you have a 1 stored here or a 0 stored here, and you have 8 other transistors that are storing that same value, when this guy disappears, it only takes one of those dudes to duplicate, right? Okay. So when we do that, we have the value duplicated. So when we have 8 transistors, that means that we can have 8 reads. And it gets a little bit more complicated than this, but let's talk about the high level because we're a little bit short on time. But so at the high level, with 8 transistors, we can handle 8 simultaneous reads, or close to simultaneous reads, at a time without having a failed read. Where we try to read a 1, but it gives us a 0, or it would actually give us a 0 if there was nothing there. So we would have an inaccurate read because the transistors couldn't refresh the value quick enough. So we kind of have 2 things competing there. One thing is that we have a maximum number of quote simultaneous reads that we can handle, and then you also have the refresh time, which should be pretty close to the speed of light, right? Electricity. Anybody know what the speed of light is? So it's just that's the constant. Okay.
299.
Yeah, it's somewhere in the ballpark of 300 what is it, 300 million meters per second? Yeah, somewhere in that ballpark of 300 million meters per second. Electricity has a speed in the ballpark of about 280 million meters per second because there's a resistance over those wires. All right, so but we can basically say it's the speed of light, right? Or as Trey said, fast. Okay, it's fast. What's up? I grade on competence, so if you just say it's really fast, that's good enough. Yeah, I don't, I'm not gonna, test you on just like I don't on the computer programming exams, what's the maximum size value to the 16-bit value you can hold. I mean, most of us don't have those completely memorized, right? But you kind of have a ballparky thing like, well, ints can hold larger values than shorts, and longs can hold even bigger ones. Fine. It's a competency-based thing. So the point is that the refill rate of restoring that the read transistor is fast, okay, but not 0, right? It's not 0 time. It does take time, which means that the time it takes us to do a read needs to not happen, needs to not conflict with the amount of time that it takes to refill the register. Does that make sense? Okay, and then there's other kind of moving parts in doing a read, because we actually need to request the read, which then goes to the CPU, which then, actually has to communicate over the bus to talk to the actual system RAM if we're dealing with well, actually this would be, if we're talking about SRAM, this is talking to the CPU, which then talks to the register. There's still some communication going on there, which is there's a delay. Again, it's fast, but not quite speed of light fast, given that it's maybe 2 or 3 steps. So we're at 3, a third of the speed of light when I guess you factor all of it in, plus you got the decision making. Like, oh, you want to do this? Okay, we'll go and do that. So there is delays in there. But that is something else we need to consider. There's going to be some sort of maximum speed at which we can read from something. And we talked a little bit about this before, so let's actually jump. Well, I don't want to jump to the technology so much, but when we're buying SSD, so we've talked about solid state drives, right? When you're buying an SSD, there's kind of 2 things we really care about. Probably the primary thing is capacity, right? But to a point. So for instance, would you rather have a 512 gigabyte solid state drive that has a 600 megabytes per second read speed, or a 1 terabyte drive that has a 300 megabyte per second read speed? Unless the 1 terabyte was really a big deal, you'd probably rather have the smaller capacity with twice the read speed, right? And then you'll just have your slower, big, giant 4 terabyte mechanical drive for, for storing your giant globs of installed software. Okay, so we care about read speed for that. So as technology gets better and better and better, our read speed gets faster and faster and faster, which then makes us go back and look at how the memory is actually implemented. If we think about that from an SRAM perspective, the faster we're able to read, possibly the more transistors we need to use, because now we need to kind of be able to, handle that impact of having a whole bunch of reads at once that are coming in very, very quickly. Okay, what's the downside of more transistors? So upside is we can have more simultaneous reads. Okay. Takes up more space. More transistors equal more space. And even though with very large scale integration, transistors don't take up a whole lot of space, because we can do circuit board printing and they're very small, but they're not size 0. They do have size to them, which then adds up, and we can only have so many transistors. Now, I think if you look at, let me bring up web browser here. Did my web browser kick the bucket? There we go. So let's look at Core i7 number of transistors. So this is, relatively speaking, new. Here. This is a 2014. You can see that the jump in transistor count isn't crazy substantial when you go through these. But this is 1.4 billion transistors on that quad core Core i7 Haswell architecture from 2014. All right, so the idea is that there's a lot of transistors. Okay, so if it takes 6 to 8 of those to represent a single bit in a register, and when we were dealing with our architecture for the DOS architecture, what was the size of AX? AX was what size register? 16 bits. AH and AL were 8 bits each. So AX was a 16-bit register. And let's use our larger value. Let's say the 8 thing here. So 8 times 16 is 128 registers. I'm sorry, 128 transistors. to represent that single value. Okay, now obviously with newer processors we have EAX and even we have 128. Actually, we have I think we have megabyte in the newest processors. I think we have 1 megabyte registers for very special tasks. But if we just think about it in terms of AX, so 128 transistors is a very, very, very tiny percent of the 1.4 billion registers that are on that the thing has. But keep in mind that the rest of those registers are part of the implementation for all those magic tricks that the CPU knows how to do. Right? Makes some sense? All right. So we don't have an infinite number of transistors, but we have a lot. But that also gives you kind of an idea on the miniaturization of transistors, where we have these little square processors, and that's probably at least twice the size of a processor. What I have there, probably about 3 times the size of a processor. So within that space, we have 1.4 billion transistors, and in actuality, it's even less space than this. Less space than a third of this, because the actual CPU die is much, much, much smaller than the square thing that is what we view as the CPU, because a lot of that is heat dissipation. Okay, but you get the idea. We're squeezing a lot of transistors into a very, very small space, relatively speaking. And we keep getting better and better and better at that. But one trend we want to see here is between 2000 and, actually this is interesting, 2010, we had a different processor here that was 1.4 billion. But when we went to 2012, we actually lost transistor count. And part of the reason we lost transistor count is because we brought graphics on board. So our modern Core i7 processors have a GPU capability on board. That doesn't necessarily replace the graphics card that's inside your machine, but it helps offload some aspects of that GPU. So we kind of have a central aspect of our processors that are really good at floating point math. It's kind of the punchline with that onboard GPU thingy.
Those ones went up in transistors,
But went down between 2010 and 2012. So this was our first introduction. Then we caught back up as we got better at squeezing things on there. Make sense? So, the idea is that, but the point is that when we see a 2012 to 2014, even though we kind of make the assumption that this processor must be better than this processor, whatever that means, right? Although I think that Ivy Bridge has a cooler name than Haswell. You think? What's the new one? There's a new one that's not even released yet for, but that's Skylake, but that's not out yet for laptops. It's out for desktops, right? Oh, do you? And don't they make a 16-core version of that? I'm pretty sure it's really sick.
Why didn't they get it? It would cost like $800
Intel CPUs. Take a minute to know. to tell us what you think. Let's see. I want desktop processors. Oh, perfect.
Not on the product page.
Oh, is this it? Oh, I was on the technology page. Processors. All right.
7 Extreme Edition, I'm guessing.
Down.
Oh, this guy? All right, well, it's... I think that's an older processor, actually.
No, those are the newer ones, I think.
Oh, could be. Yeah. 10 cores. I really thought I read about one that had more. So, yeah, because it's hyper-threading. That's hyper-threading is kind of a pipeline technology like we talked about. So, every core is 2 logical cores, as they kind of call it. So this is 20 logical cores in this this CPU. Maybe I was looking at something like this. I had 16 logical cores. Maybe it was this one. Yeah. So here's a 10 core model of that guy.
AMD doesn't really do hybrid.
They have kind of an equivalent pipelining technology. What do they call it? They have a cool name for it too. I don't. It's slipping my mind right now, but yeah. They're competitors, right? They try to do something similar. But yeah, so you can imagine when that we're getting 10 physical cores on these machines today, as opposed to the numbers we looked at here were quad cores. Okay, so chances are, though, we haven't necessarily greatly increased this transistor count. Right? We can kind of see here between 2010 and 2014, we didn't make jumps really. We assumed that in there was, this guy was a little bit faster than the previous guy, so we learned how to do more with the same number of transistors or something like that, But the punchline kind of being that we seem like we're hitting a wall on what we can do directly with hardware in terms of how much stuff we can squeeze onto the CPU, which is why we're starting to look at some newer technologies. One of the grad students in the 548 class, which we're doing some research projects in there, kind of like this class, but the second half was a research course. He's looking at the implications of optical computing over silicon-based computing, which reduces the heat to almost nothing. So more transistors equal more heat, which means more heat dissipation that we need. But we also, with each new processor that comes out, one thing we might notice is that it's not on this chart, and I think that the other thing we had pretty much shows their current line, so all the wattage is the same. But this wattage, 140 watts, is down from previous iterations of processors. So the processors are becoming more and more memory efficient, kind of maintaining transistor count, getting, quote, faster for typically specific tasks. So when a company like Apple says that, our new laptop is, more than 4 times faster than the, last year's model or something like that, it's probably in a very specific test. Where one piece of their software that Apple wrote really takes advantage of one of the new or updated magic tricks on that CPU that just looks awesome. One of the examples I'm thinking of is years ago when this was when we were still PowerPC RISC processors in Macs. The 1.4 gigahertz G4 processors that came out, and it had a technology on it called ALTIVEC. ALTIVC. Yeah, so it was a thing that was on those processors, and I had a machine that had a dual CPU, not a dual core, but a dual CPU, G4, and we were running distributed.net. Distributed. Let's see if this is even still a thing. Yeah, oh, it's even still the same site. Yeah, so interesting. So distributed.net, this was kind of one of the early things, like you've probably heard like SETI at home, where you help search for aliens and that stuff. So distributed.net, the goal of this project is to use distributed computing to crack encryption algorithms. Okay, and so like the geek competition, like today we're all playing video games and stuff like that, but back then, my friends and I, we were like, well, how many tests per second are we doing because effectively you're generating, there were key servers and you're trying to crack the encryption algorithm with these keys. And it's, the idea is that every encryption algorithm, if you've had the security class, the idea is how long would it take to do a brute force attack? And if it could be more than like 3 generations or something like that, then we're going to consider that secure. Well, what does that mean anymore if you have 5 million computers all working on it simultaneously? Something like that. Well, when the G4 came out, that machine did that type of math like 30 times faster than the previous processor. It was like ridiculous. So I had a pretty big jump in the speed I was doing just from a processor that for almost every other thing wasn't so, ridiculously faster. So AltaVec would be like an updated magic trick or an updated way of handling a certain magic trick, which more than likely these companies, when they come out with a new processor or a new laptop and they claim how much faster it is than last year's model, they're pointing at a very specific example. In fact, I've seen some other examples, especially with them. Because I have one coming, I've been looking at a lot of the reviews for the new MacBook Pro, and I think there's several things that it actually is performing worse than last year's model for some things, unless you're running Apple software, which is like way better, because Apple did something with the new magic tricks or something like that. But I guess whatever. Plus, why does somebody need that big of a trackpad? Like Apple talks about this thing as like a big feature that the new MacBook Pros have a trackpad that's, I don't know, the size of a state. I mean, have any of you ever sat there in your laptops and just said, this trackpad's just too small? Is that like something you think about? It's like,
I also didn't think about
he's complaining there's even a trackpad. Like, why are they wasting this? I mean, that's valuable sticker space, is what this is. I mean, I like the trackpad, but I mostly use it for, swiping between screens and stuff like that. I don't want to have to do this, this giant rake maneuver. So I just don't get it. I mean, why? Do we have a theory as to why we need such a huge trackpad? Is Apple looking for two-handed gestures? Because nobody uses...
They're just trying to get it to where they can put an iPad down there also.
They're going to replace the trackpad.
3 times,
Yeah.
3 times.
Yeah, the next version, they actually replace this larger trackpad with an iPad mini, which has a touch sensitivity, so it can be in... You launch the trackpad app. It's a context-sensitive trackpad app. Okay, otherwise you can play Angry Birds. Well, yeah, isn't it the new Nintendo? It's what's it called? The Switch. Yeah, they had that on Jimmy Fallon last night. Yeah, where it's like 3 machines in one. You can be playing on your.
It's gonna have GameCube backwards compatible or emulator also. So you're gonna play GameCube games on it.
Yeah,
It's like an auto buy. I don't know how you don't buy that.
I guess it depends what games you're into. I mean, Nintendo's always been more party.
All of them that are going to be on the Switch. All of them.
Yeah, but Nintendo's always been more of a party game type thing. Where
party kind of guy, just Mario Party.
So you play a lot of Mario Kart, right?
Nah, I play Smash Brothers.
Smash Brothers, yeah.
There aren't many people that play it anymore.
Oh, because you're really good at it, I'm guessing. I think Schumacher's supposed to be pretty good at... didn't they have some sort of I think they had like a tournament or something here on campus. Was it last year?
What, Mario Kart?
No, I think it was Smash Brothers.
Yeah. I remember hearing that.
Yeah. Well, I mean, he spends all his time playing video games. He doesn't do school. It's like, well, I got to skip class today because I'm live streaming. I'm live streaming me live streaming a game. So, who knows? All right, so let's bounce back here. All right, so the idea is we have a zillion transistors, relatively speaking, on our modern hardware, but we're not really figuring out ways to get more transistors on there. Yeah. Shut up! I just love that reaction.
So unexpected.
I knew it was coming. I was like,
it's so unexpected.
the story he's telling is like 5 minutes long. I'm like, you're going to yell at him.
Yeah, that's my lead up move. All right, so we have a lot of transistors, but we're not getting better. We're not getting better at adding transistors, right? So we're kind of hitting that end of what silicon-based chips can get us. So we have to start looking at other options. At some point, adding more cores doesn't help. Like we just looked at there, we have effectively a 20-core processor. Okay, very rarely are we going to do something that's going to really take advantage of having 20 physical cores. Make sense? All right. So You know, when we look at flash memory, we're really looking at read speeds, where, you know, SRAM, our capability read speed is really speed of light, minus that time it takes to request the read. Okay, whatever that means. Okay, so let's go this route. DRAM. How does DRAM differ from SRAM?
Single transistor per bit, but uses a capacitor to store the value.
Okay, so we have one transistor plus one capacitor to preserve a value. Well, let's go with that. So a DRAM, well, this is per bit. All right, where all those up there were also per bit. So one thing we noticed already, I mean, we would expect that DRAM would have larger capacities than SRAM, right? And part of that is because, well, we just looked at an example there with processors that, you know, we can squeeze a whole bunch of transistors into a, you know, some space. And, you know, capacitors, whatever their size is, you figure that one transistor plus one capacitor probably takes up less space than 8 transistors. Let's just use that as a, you know, we'll use a tray math here and just say, well, it's fast, it's, you know, relative size, it takes up less space. How much less space? Who knows? Well, somebody knows, but, you know, whatever. All right, so this guy takes up less space, which means we can put more. We can represent more bits in kind of the same physical space. All right, so now that's why we can have, you know, an 8 gigabyte chip as opposed to a, you know, 1 megabyte super register on our CPUs, that kind of stuff. Or even if we go to some of our cache-based technologies that are kind of SRAM hybrid type things, you know, we're looking at 2 or 4 megabytes of cache. We probably saw that over here. Yeah, we see the, so I mean, this is a lot of cache. 25 megabytes of effectively SRAM hybrid memory. This is pretty fast memory sitting on the CPU. So we get a lot of our speed from proximity, and then we also get quite a bit of speed from the memory technology that's under the hood. But 25 megabytes, when we see that number, we don't think of that as being some gigantic number, right? 25 megabytes, whatever. That's huge for CPU cache memory. You know, we go down to, well, actually, all these are pretty big. You know, historically, what was considered to be relatively large amounts of cache, oh, this was our extreme processor, right? That's the one we picked. So let's go down to a more normal processor. 7th gen Intel Core i7. Here, let's go with that. Yeah, so here, we got 4 megabytes of cache. All right, and 4 cores. So this is, but notice the wattage. You know, comes. This is probably one that's really based for mobile devices. You know, but the.
There's one below it for desktop.
Oh, thank you. Let's see what the. But even these, the power consumption is. Well, actually, these are. Oh, this is the 6th gen. So this is a newer processor for mobile. But in any case, we see that the power consumption is less than the Extreme. All right, so, you know, whatever, but everything else is a lot smaller on them. But that doesn't mean that these are substantially slower for the average applications. Okay, so this is much more normal cache, 4 megabytes of cache. Okay, so we have 1 transistor plus 1 capacitor, so we have more real estate to work with for representing bits. Great. What about speed? What about read-write speed? Which is faster, SRAM or DRAM? SRAM. SRAM's faster. Okay, why? What makes DRAM slower than SRAM? Okay, well, so it relates to the capacitor. So, go ahead. It does have to be refreshed periodically, but sometimes that doesn't translate into read speed because it could happen while we're not reading from it. Okay.
It takes a while to drain the capacitor.
Yeah, time to read from a capacitor is slower than reading from a transistor. You know, it takes less. It takes more time. So you have some, if we're trying to make that memory faster, what are we doing? We're trying to find faster ways of draining a capacitor, which is what probably ultimately ends up meaning using smaller capacitors. Well, because smaller capacitors have less energy stored in them. Think of a capacitor as kind of like a water tower that holds energy. Like you go to like a city that has the big water tower. You think about bigger water towers that's going to take longer to drain all the water out of it. All right, so smaller water towers are going to have the water drain out of them more quickly. Fine, that seems good. What's the bad thing about having a smaller capacitor when it comes to DRAM? Yeah, so really, it's the combination of what you guys were saying. It's if we have to periodically refresh it, there's a natural drain to a capacitor, and the smaller that water tower, the smaller the capacitor, the more often we're going to have to refill it, right? So now it takes some extra babysitting to do that. So somewhere you have to find that sweet spot, right? What's the largest we can make the capacitor while kind of supporting maintenance time relative to read time. That makes some sense? So, and this is really indicative of technology in general. As we go through and look at kind of the history of technology, it's always about playing this balancing act between, heat and what kind of technologies we use in something that allows us to get speed plus power consumption plus blah, blah, blah. And it's always this balancing act. We find better ways of doing certain things, and we just saw some of these processors that each year Intel comes out with a new processor in the same class processor, 6th generation versus 7th generation. You usually see a reduction in power. Okay, they're drawing less power to do, let's call it, relatively the same thing. So we're getting better at those things. But what we're seeing in recent years, and this goes back to what we talked about a few minutes ago with the whole silicon, we're starting to hit the limitation of that guy, is we're making less leaps. We're not jumping in terms of technology anywhere near like we were in the earlier days of technology. Let's take the 90s and the early 2000s. One of the things your book talked about was Moore's Law, right? So what is Moore's Law? What's that guy roughly say? We read about it, right? It was in there? Okay, by how much? Yeah, roughly. So if we were to give kind of a generic example, is technology roughly doubles. You could say every year, every 8 months, whatever. So I've always kind of thought about it as every year. Every single year, speed doubles, capacity doubles. All these things double. And that was a true statement in the late 90s, the early 2000s, right? Processors. So in 1996, I had a 66 megahertz processor. Forget about the underlying architecture. That was a DX2, 486 DX2 processor. So forget about that underlying architecture. That, as they came up, they got faster. But, look at that clock speed. That clock speed is effectively the number of instructions it can handle per second. Make sense? That's not always the best way to measure processors because the architecture does play a role. But if we just kind of operate at a 2,000-foot view here, and we just compare clock speed and pretend like the architecture remains the same, how much, what's our speed in our processors today? 2.6 gigahertz? Okay, how many megahertz is 2.6 gigahertz? So 2.6 times 1,024. So that's 2,662 megahertz.
Is that how megahertz is calculated?
Yeah. Yeah, it actually doesn't do the 1,024 thing. It's actually usually when they measure it, it's 1,000. This is close enough. So I just wanted to keep it consistent for our 1,024 jump. All right. So 2,662 megahertz. So if I divide that by 66, that's 40 times faster than a processor from 1996. 20 years, 40 times. Now, yeah, it kind of messes up a little bit because, you know, you have the cumulative effect that kind of goes with the exponential growth type thing. But, and like I said, there's an architecture difference in there as well. But if we just take the numbers flat out, 40 times faster is a lot faster, right? Using tray math, okay? It's a lot faster. So we've gotten much, much, much faster since 1996. But what if we look at our processors since 2010? In 2010, you could have gotten a 2.6 gigahertz processor. In 2016, you can get a 2.6 gigahertz processor. All that's really changed is the underlying architecture, and then we have some of that speed boost stuff, right? You know, because really, when we talk about clock speed, you know, what we're talking about is kind of cruising speed of the CPU. When I say how many of you have ever overclocked a processor or overclocked a GPU? Okay, what does that mean? What does it mean to overclock something?
Say go faster.
Say go faster. And what's the risk of going faster? Overheating is the major risk. I think I've told the story before of the guy who lived down the hall from me. It lit his room was pits of hell. I mean, it was on fire, not small fire. Flames billowing out of a dorm room. The whole room was on fire. Paint lit up, everything. And that was overclocking. I think it was a 600 megahertz Celeron processor to something like 2.0 gigahertz or something like that. Okay, and this is in 1997, maybe 1998. Somewhere in that ballpark. That's a lot of overclocking for something that wasn't meant to be overclocked like that. So heat's the biggest thing. Now, what else? You said it degrades the life. Obviously, that's heat related. But you also have accuracy issues, right? That processor wasn't rated at 2 gigahertz because it couldn't operate at 2 gigahertz safely, heat-wise. But it also couldn't operate at 2 gigahertz accuracy-wise. Okay, and that kind of relates to what we're talking about here. Reading from memory, you know, if we're handling, you know, two, let's say, million instructions per second. Let's just use this as an example. If we're operating at that rate, that means we need to be able to read. Since a lot of instructions relate to SRAM, relate to a register, we need to be able to keep up our reads at that, right? Well, SRAM, can we assume that in 2000, SRAM technology wasn't quite as good as it probably is today? Reads were slower than they are today, so we couldn't keep up. That's a problem. Okay, so punchline is when we overclock, when a processor says it's 2.6 gigahertz, that's the speed it can operate at without fail. Okay, if you take a network class and we talk about the handshaking when a modem is connecting, you hear all the beeping and all that stuff. You know, that's before TCP/IP. So those two modems are negotiating a maximum speed at which they can talk to each other without screwing up. All right. So this kind of supports Dr. Locklear's approach to the grand ideas of computer science. We have these common themes, regardless of what kind of topic we're talking about, whether it's networking or security or programming or architecture. It's the same stuff repeated. That kind of makes some sense. So our punchline is that more recently, what have we gotten better at? You know, we said, well, it's a 2.6 gigahertz processor, but it could turbo when necessary to 3.3. It's a sprint, okay? A small burst of speed for a controlled amount of time until, we start seeing the red lights going off about heat and stuff like that, then it throttles back. So when the processor needs to be faster, it kicks it up a notch, right at the end of that race, right? You break into your sprint, yeah, but you couldn't maintain that the whole race, otherwise you would have. right? And then you'd really win, right, by a lot. Okay, so the punchline is that's what the processors have done today. They've gotten better at safely overclocking themselves without serious damage and heat problems and that kind of stuff. But certainly we're starting to hit this limitation of what we can do with our current technology. So Moore's law really does not apply to our technology today. Is that a fair statement? But what we keep coming out with is innovation. So, when we're comparing, Moore's law really applies to speed of similar technology. Okay? And we probably are. If we're following Moore's law to some extent, we're probably best keeping up with it in terms of read-write speeds. So read-write speeds of flash memory probably is doubling every year, or making a pretty good stab at it. We're nowhere near. Well, that's probably a too generalistic statement. We are not at the fastest that our solid-state drives are going to transfer data. We got room to grow there. Our Apple's new solid-state drives that are in the new Macs are pretty impressive. Those have a really fast read-write speed. But everybody else is going to have them too in a week. But next year, those speeds will probably be mediocre plus or something like that. We're going to keep getting faster in that regard. But we're already way faster with SSD than we were the previous year. All right, so the idea with DRAM is we get a lot more capacity. But what we do is we give up some speed because the time it takes to drain a capacitor is too fast, is high. And then we can try to play tricks on managing the size of the capacitor, finding ways of draining it more quickly, whatever. That's where we're picking up our non-Moore's law-esque speed increases, right? Because we're at a limitation of our technology today. So I was mentioning a few minutes ago that one of our grad students is looking at optical computing and what that might mean. And it has its own limitations right now, mostly dealing with cost, but that's normal, right? Whenever a new technology is introduced, it costs too much. But eventually they usually take up more space too, but we usually figure out how to make them smaller, make them less costly to produce, and blah, blah, blah. All right, so DRAM, slower than SRAM, bigger capacity in SRAM, and really it's a lot slower than SRAM, right? I mean, the time it takes to drain a capacitor is way, way, way slower than the time it takes to read from a transistor, okay? And that's rounded down using tray math, okay? Way, way, way slower, right? All right. So, now what about flash memory? How does flash memory differ from those first two?
Two transistors that are in it, and then also two gates, and there's electricity that's stored between the two gates so that it can keep the value when there's no power.
Okay, so one of the nice things about flash, typically we see flash today in our hard drives, but we've seen them in our the sticks that we put in. Well, we have our USB sticks, which is flash based, and then we also have the stuff that goes in there like digital cameras and that kind of stuff. But these, probably the biggest benefit of flash, especially for mobile, is no moving parts, right? If you drop your cell phone, you would have to drop it hard to damage your storage on your. We're talking about a spike, and even then, you're gonna have to bend the frame and actually get to that chip and break it in order to damage the storage, because there's no moving parts in it. Where if you had a mechanical hard drive, you're not gonna have to drop that thing that hard to damage that guy because of the way they work. All right, you're gonna shatter the screen on your device. That's how your phones break, right? Right, Curcio? Is yours front and back or just the front? Just the front. All right, so flash memory has the no moving parts benefit, okay? It also has the benefit of when it doesn't have power applied to it, it can maintain a charge. It's a hard drive-ish type technology. it accomplishes that with a few transistors, and it really depends on the actual flash technology. Some of the faster ones use actually more transistors to kind of help with that speed because they try to act like kind of SRAM-ish, SRAM-esque-ish, esque-ish. They act SRAM-esque-ish. Yeah, 2 Z's. All right, so let's say we have 2 transistors, and then we have a couple of gates, and those gates try to maintain a charge between them. Okay, and that charge gets maintained even when power isn't applied. Okay, so it almost tries to implement a capacitor without a capacitor, right? And we have the benefit of no drain. All right, so let's do a couple of gates for simulating. Yeah, let's go with it. Capacitor. I'm surprised I let that fly. For simulating a capacitor. Now, what's the weakness of flash memory? Okay.
Doesn't it damage the cell?
Yeah, it can wear out. Yeah, it's like kind of like tennis shoes, right? You know, we all have we call them tennis shoes or sneakers. What's the modern word? Just shoes. We know you have your sports shoes, right? We don't call them.
I think those are like the new like. Well, most people wear like running shoes nowadays anyway.
Really?
Yeah. Like all the time.
So tennis shoes doesn't make a.
I don't wear running shoes all the time. Never.
Huh. Well, in any case, when you're wearing your shoes eventually wear out, right? But most of us we have a wear pattern, right? You kind of always wear your shoes out in the same place depending on how you walk and you know where your weight is and that kind of stuff. So you know, the rest of the shoe looks untouched except for that one spot where it's like worn to the sole or something. All right. So Flash is kind of like that, where several read writes they damage the medium. They damage the cells. Okay, well, so you know that the actuality is that flash memory does actually have a longer life than our mechanical hard drives. Not by a lot, but it is. One concern we might have is, oh, well, we're getting a whole bunch of speed here, but the life of this guy is half. That might be a concern we would have, right? Okay. But the reality is that our modern SSDs have a longer life, maybe 10 or 15% longer than a mechanical hard drive. Okay, but part of that is done by us kind of having a strategy for maintaining the wear pattern, making them wear kind of evenly. So instead of having that shoe that wears down just on one edge, we have something that wears kind of evenly. How does that work? I think it was in the book, right?
Yeah, leveling.
Leveling, okay. And what does it ultimately do?
Basically, it looks, when I was writing stuff out, it looks for cells that haven't been used yet.
Mm-hmm.
So it distributes evenly.
Yep. So it's almost like real-time defragmenting, right? So, you know, we're mostly familiar with the idea of like, oh, I'm going to defragment my hard drive and it takes a month to do, where it kind of, you know, typically defragmenting takes your mechanical hard drives and it moves the data towards the beginning to benefit read speed. You don't have to go out to the boonies to read something. It kind of moves everything up front. Well, real time, we're going to call it like defragmenting. We're in that we're moving stuff around. You know, its idea is that, hey, you know, we've done a lot of reads here, so let's take that data that's stored there and let's actually move it here, remap it, so the next time we read or write it, we're reading and writing it over here, evening out the wear. Okay, that kind of makes sense. And flash is going to be the slowest of these 3 technologies, but it also is going to have the largest capacity. You know, today we complain about our solid state drives being too small. Didn't you say you had a 64 gigabyte solid state drive in your machine? 128, okay. But in the big scheme of things, that's a small hard drive by today's standards, right? Okay, but so that's why he has to pick and choose what he puts on that guy. because he's got a limited capacity. Well, do any of us have 128 gigs of RAM? No, not even Doctor. He's not here today. He skipped. Okay, but I think he has 32, right? I think he has 32 gigs. They could. Well, no, we're not talking about. I mean, that wouldn't be an overclocking thing. We're talking about memory capacity, and memory capacity in a machine. I mean, you have physical slots. How much physical memory can I stick into a machine? But in terms of our 64-bit operating systems today, they can address. I think it's 2 terabytes of RAM. No, it's more. It's 16 terabytes of RAM. They can address 16 terabytes of system RAM, if we could somehow squish that into the machine. So we're not maximizing the amount of RAM that we know how to address. And what I mean by address is uniquely identify this address from this address, this address. Each of those addresses, in our bits. Usually, when we're dealing with memory technology, we're not reading bit by bit necessarily. We're reading clusters, especially when we deal with our kind of flash memory and most of the DRAM technologies. We're reading a cluster of megabytes or something like that. So the idea here is that those guys, we need to be able to uniquely tell the difference between the position of this guy and the position of this guy. And we have a whole bunch of RAM. We have a whole bunch of unique addresses. It's like a really, really long street with a whole bunch of houses on it. And if we can't count that high because the number doesn't fit inside of a 64-bit unsigned integer, then we can't address that much. All of a sudden, the houses way at the end of the street don't have addresses anymore because we can't count that high. Does that make sense? So with today's memory, today's 64-bit memory subsystems, which was an operating system concept. With that, we can address 2 to the 64th unique addresses, which is so 2 to the 64th. So that's a giant number. So that's unique, and then you divide that by the size of each bucket, and I think for modern DDR3, it comes out to 16 terabytes of RAM you could address. About 97.25% confident on that number. Okay. So does that make some sense on our differing technologies with memory today? Kind of takes us back to near the beginning of the semester when we talked about kind of the relative speed of memory. And then we kind of bookend the semester by saying, okay, well, here is how those memories actually work and why the relative speed is different. Without getting in there and actually soldering transistors and stuff like that. So we got that high level view of how those technologies work. All right, so for the exam, definitely be familiar with these 3 different guys. Be able to speak intelligently about them. So for example, I used that, in this discussion we had today, we talked about, what are strategies for making DRAM faster? Well, you can shrink the capacitor. What's the trade-off? What's the cost? Be able to tell me that the cost is, okay, well, now we need to maintain that smaller capacitor, that smaller water tower by refilling it more often, okay? Which maybe takes more energy or something like that, or at the very least takes more time. For hibernation, your laptop needs to wake up more often, that kind of stuff. All right, so kind of understand the pros and cons of these things. SRAM, number of transistors drives the number of the number of simultaneous reads. All right. Well, at the same time, there's going to be with today's technology, there's going to be some sort of maximum based on just time. How many simultaneous reads is even possible? We don't need more transistors than that, right? You don't need to have 300 transistors on there to support 8 simultaneous reads. You need 8. All right, and as our ability to read more quickly comes, then we need to get more transistors on there, which then means that we need to get more memory, fitting in the same piece of real estate. Otherwise, we need to make our processors bigger for the registers and that kind of stuff. All right, so understand the nuances of those three technologies, because the questions I'm going to ask aren't going to be like, tell me how SRAM works. It's going to be a more specific question about SRAM like we've discussed today. Okay, which is why I don't really feel bad about the open book thing, because I'm not going to ask you to regurgitate stuff. Could be a question on Moore's law, but it would be more along the lines of maybe kind of like an essay type question about, discuss the challenge with Moore's law today, and how things are getting, not getting faster as quickly as they were before, and why is that? Limitations of silicon, not being able to fit more transistors into the same space, stuff like that. Okay. Be able to speak intelligently about our mechanical hard drives, but at a much higher level. We really focus on these three underlying technologies, because mechanical hard drives are more of a museum piece now in terms of the underlying technology. They're not really a focal point of improving. Our focal point today for hard drive stuff is SSD. I don't think we're going to really see mechanical drives get significantly larger in capacity moving forward, because what we're trying to do right now is we're trying to make the SSDs catch up. Because ideally what we'll have in a year or two is, in his computer he won't have 128 gigabyte SSD and then a 2 terabyte mechanical. He'll have 128 gigabyte super fast SSD and then a 2 terabyte less fast SSD. That costs less per gigabyte and that kind of stuff, but it's still way faster than your mechanical drives, blah, blah, blah. Let's see. Be able to do kind of conversion math like this. If I give you a transfer speed of some file, I might ask, how long would that take to transfer to disk? If the write speed was 600 megabytes per second and you had a 2 terabyte file, how long would that take to write to disk? Be able to do that math. Some of the modem stuff we talked about, analog versus digital. Understand that the nature of those technologies, difference between dial-up and DSL, that concept of handshaking we talked about, which is really a networking type concept, but we applied it in here from the perspective of kind of the grand ideas type thing. DSL versus cable, to an extent. I'm probably not going to spend a lot of time, like what was the weakness of cable initially. They had to have a modem because it couldn't do two-way communication. That's more trivia type knowledge. So really, I'm going to focus more on nature of analog versus digital in terms of those electrical signals over a copper wire. Analog is a wave that needs to be then converted back into digital, and we can only do that so quickly. Where digital is showing up in zeros and ones and can be read directly without conversion, which means faster in tray speak. We at the high level, we talked about data representation and hardware. How do we represent zeros and ones? We've looked at three approaches: the SRAM, DRAM, and flash over the last week or so, which is kind of our current model for that. But when I say something like data representation and hardware, how do we represent values? Or we can look at a single bit as a value. How do we represent those guys? And what are some things we can play with? I might give you a question that gives you kind of an arbitrary example and ask you to give me a using kind of our registers and stuff like that, give me a way that we can represent the certain output, putting together, like when we did in class, like kind of building an adder, those kind of things. I probably wouldn't ask you to write something that complex. I might give you kind of a simpler truth table and say, create a circuit that would do that would give you that output, kind of understanding how we can represent an idea in hardware. That was kind of based on the whole idea of JSON versus XML. I could ask how transistors work. I wouldn't get into tons of detail, but you should understand that slide. the idea of vacuum tubes and how they relate to transistors, certainly. And I'll go pretty quick here, so I know we're out of time. Yeah, I mean, I'm a big fan of conversion type questions, so you should be able to add binary numbers together. You should be able to subtract binary numbers using 2's complement, those types of things. Understand the concept of a half adder versus a full adder. I probably wouldn't have you design one, although it wouldn't be that big of a deal since you have your notes. But understand that one of them takes a carry bit, the other one doesn't. Understand the concept. If I asked you how many half adders and how many full adders would it take to represent a 16-bit number, adding 2 16-bit numbers together, you should know that you need a full adder for the far left bit. You can use half adders for all the other ones. Actually, no, other way around. Because well, unless you need a carry, then you'll have full adders everywhere, half adder for the very first. But understand the difference between those guys. All of our gates, be able to recognize the pictures of them, what they look like. That's kind of how our hardware is made. All right, and then everything else would be kind of what I said was important for the midterm. I'm probably going to focus on some assembly questions. I probably won't spend a whole lot of time talking about some of our early stuff that we dealt with. The idea of a CPU being a collection of magic tricks, stuff like that. We kind of should have that by now. All right, so look for assembly stuff from the first half of the semester and then what we've talked about today for the second half. Make sense? Questions, comments, concerns, bribes? All right, I'll see most of you next semester.